In this video, we're going to learn what happens to the interval of convergence in a series when we take the derivative or we take the antiderivative. So in a previous problem, we had looked at this function, x to the n over n, and we had figured out that the interval of convergence is from -1 to 1, including -1, but not including 1. So now what we want to do is try to figure out what happens if I try to find the interval of convergence of the derivative of this function. Now we can take the derivative function of a sigma like we do anything else. N is just a number, it's just a counter, so I'm going to treat it as a number. So when I take that derivative, I'm going to bring down the power, reduce the power by 1, the n on the bottom still stays. Notice this will drop out. So this is your sigma for f prime of x. So in order to find the interval convergence, I'm going to go ahead and do the ratio test. So ratio test says if I take the limit of the n plus first term, notice if I plug in n plus 1 here, though, it becomes n plus 1 minus 1. So really, I just end up with x to the nth divided by the nth term, which is my original, and this is what I get. Okay. Now, if you simplify this a little bit, this is really x to the n, this is really x to the n times x to the negative first. This will drop out. This is going to go to the top. So your limit ends up being the absolute value of x. Ratio test says it only converges if that is less than 1. So this is my inequality. Now I'm going to go ahead and check the endpoints. So let's start with x equals 1. So remember, I'm going to plug it back into the original sigma. So if I do that, this is going to give me this. Okay, this is really a geometric series that diverges because it's really 1 to the n times 1 to the negative 1. This is just a number. This is being what's raised to the nth power, so your r is 1. This is a geometric. We're going to say it diverges. Let's see what happens when we have -1. So same thing. I'm going to plug the -1 in for x here. So if I do this, same thing happens. Your r is -1 this time. Still a geometric, still diverges. So your interval of convergence for the derivative of that original function is actually -1 to 1, not including either endpoint. Let's see what happens when we integrate the function. So the integral is going to be, we're going to add 1, divide by the power. That n on the bottom of the original is still going to be there. So this is my sigma of the antiderivative of f of x. So again, I want to find interval of convergence. So I'm going to go ahead and do my ratio test. So limit as n goes to infinity of the n plus first term. So this becomes n plus 2. This becomes n plus 1 divided by the original. I'm just going to multiply by the reciprocal. So I have this. So there's my setup of the ratio test. We can simplify a couple things. The only thing that simplifies is that x to the n here, the x to the n here. You have x squared on the top, x to the first here. So all you're really left with is an x. This is gone, so I have this. You're taking the limit as n goes to infinity, same degree, so the ratio of the lead coefficients, you're just left with x again. So again, this is my ratio test. Says it only converges if that is less than 1. So there's my inequality. I need to check the endpoints. So let's go and start with x equals 1. If I plug in x equals 1 here to the original, you're going to get 1 to the n plus 1 over n plus 1 times n. Now, 1 to the n plus 1 is just really 1 on the top. This on the bottom, you can think of it like this. What do we do when we have powers on the top, powers on the bottom? We're going to compare to a p-series. I know this is going to converge by LCT because we're comparing to a p-series that converges. Let's go and check -1. I'm going to plug it in for x. Okay. Here, I'm going to use alternating series test. And remember we talked about if all you have is n's on the bottom, I know this limit's going to go to 0. That n plus first term is going to be less than the nth term, so I know this is also going to converge by alternating series test. So this interval of convergence looks like this. It's from -1 to 1. but including both endpoints. So the conclusion is actually that when you look at an original function and you know that interval of convergence, the only thing that's going to differ, this limit is going to be the same. So the only thing that differs is the endpoint. So that's really all you need to check. Just the endpoints are the only thing that might differ.